thank you for the great talk. And today I'm going to present my previous work on task performance and model calibration with supervised and self-ensemble in context learning. And before I start my talk, I'd like to thank a group of fantastic collaborators, Han, Goran, and Yvonne. And I have to admit that this work is not really relevant to the multimodality, but may be of interest to the research community as well. So currently, the foundational language models has already achieved relatively good in-task performance with in-context learning, where the context could be few short examples as demonstrations or task instructions, and the contexts are concatenated at the very beginning of the text input. And on the bottom right side, you can see a screenshot from Llama 3, which is newly released just a few days ago. And with 70 billion parameters, we can see that the performance has already reaches up to 80% or 90% of accuracy. So here comes a question for us. Since the foundational language models has already achieved relatively good in-task performance, what's the next step? Are they really ready for real-life applications? To answer this kind of question, we have to first figure out one thing, which is, to what extent can we really trust the system predictions? Are they really reliable and trustworthy to us? So here's an example. So let's suppose the task is to determine the sentence sentiments into hate, support, or neutral, these three different classes. And let's suppose there is a hate speech detection system, which currently gives, let's say, 60% of accuracy. And now here comes the input sentence fed to the model, and the model would output a distribution over all possible candidates of the label space. And the model says that now I have 75% of confidence saying that this sentence is support. So can we really trust this system where the confidence actually surpasses the mean accuracy of the system? And if we treat the accuracy as the probability of the model getting correct, the answer seems to be no, because it seems that the model is overconfident about its predictions, making it less trustworthy and reliable to us. So this brings about to us, so when we evaluate the models, it has to be more than performance. So here comes the calibration. So what is calibration? I don't want to give you a really long and verbose definition about the calibration. Generally speaking, a well-calibrated language model should be accurate in terms of both performance and while also producing reliable confidence estimates for the predictions, which means that the system or the model should not be too overconfident about its output. And the problem overconfidence is even more severe in limited data settings. So in this case, the research question of this work is, can actually large language models achieve calibration with in-context learning, especially in the limited data settings? So to answer this really huge or broad research question, I decompose this to two sub-questions. The first one is, how would in-context learning impact the calibration of the model? And the second one is it really possible to ensure both in-task performance and well-calibrated language behavior at the same time? And to answer these questions, we have to first figure out how we are going to measure or evaluate the calibration of the language models. And in this work, we adopt the expected calibration error as the main measurements. So expected calibration error, short as ECE, describes the calibration with the absolute difference between the accuracy and mean confidence of the predictions. And if we take a look at the right diagrams, the ECE is represented as the pink area in the diagrams. And we can see that the diagrams on the right have a smaller pink area than the left, indicating that the system of the right diagram is more trustworthy than the system on the left. And for simplicity in discussion, we define this work that the system with ECE less than 0.2 as calibrated system. Now, for experiments in this work, we mainly compare 4 different kinds of learning paradigms, including zero-shot learning, in-context learning, supervised fine-tuning, and supervising context learning, where the first 2 learning paradigms are inference-only methods, but we still adopt learning in accordance to other learning paradigms. And the latter 2, supervised fine-tuning and supervising context learning, are tuning methods which really requires to tune the model's parameters. And to clarify that, we still include the zero-shot learning and supervised fine-tuning within the framework of in-context learning, because here, the zero-shot learning and supervised fine-tuning, they still include the task instruction in the front of the text input, which is in accordance to our definition of the context at the very beginning of this presentation. And we compared these 4 different learning methods in a total of 7 different classification data sets, with Flan T5 large as the main backbone model. And each experiment is conducted 3 times with different random seeds for general reliability. So, for the first research question, how would in-context learning impact the calibration of language models? Through extensive experiments, we found that the language models with different kinds of learning methods is actually not necessarily calibrated, despite of the high in-task performance. We observed that on SST2 and RTE, the model achieves high performance, but it also has high ECE score as well, which indicates that the prediction is not as reliable as we thought it should be. And with zero-shot learning, only on SST5 the model is calibrated, and with supervised tuning methods, the model indeed achieves high performance, but also becomes less calibrated on some of the data sets. And if we summarize all these findings based on the tasks, we find that the performance and the calibration of different learning methods are actually task dependent. For example, for certain tasks like SST2 and RTE, the model with in-context learning actually can achieve comparable performance without tuning any parameters, and also they achieve lower ECE score as well. But for some of the data sets, such as NLU++, manifestos, and hate speech, the model with in-context learning cannot be comparable in either performance or ECE. So that comes to the third one. And if we take a step further, we actually find that this task dependency is determined by whether the data has been seen by the model during the training. And for the data who has been possibly seen by the model during pre-training, the in-context learning inference-only methods can achieve comparable performance with supervised tuning methods. And we suspect that that's possibly due to the data contamination of the training corpus and the texting data set, which corroborates with other research in the data contamination research community as well. But for the data that has not been seen by the model during pre-training, the in-context learning's performance cannot be comparable with supervised tuning methods. So we actually do have some ideas about how we should choose the learning methods when we have the data. For the data that has been seen by the model, maybe in-context learning combined with other tricks such as batch calibration may be a better choice to try first. But for the unseen data set, supervised tuning methods may perform better and deliver more trustworthy predictions than the inference-only methods. And if you're interested, you can see on the feed from the table on the right, for SST2 and SST5, these 2 data sets are possibly seen by the model during pre-training, and after applying batch calibration, the performance is comparable with the performance of in-context learning is comparable with supervised in-context learning, whereas it's not the case for manifestos and hate speech. So far we have observed the common miscalibration issue across all different learning methods. Then comes the second research question. how can we ensure both performance and calibration at the same time? So in this work, we explore the feasibility of using self-ensembling pipeline, which is illustrated on the right. This is really simple pipeline. So we have the predictions with different variations to the input, and then we run several different kinds of self-ensembling strategies from a single model in order to obtain the final predictions or the final probability distribution over all the label spaces. And then we would have the final output. And for the variations, we introduce or investigate different types of variations in context examples and different phrasing in prompting templates, and also combine both of them. And for ensembling strategies, we mainly investigate 3 different strategies: majority vote, and mean probability, and max probability. I'm not going to elaborate a lot of this on the strategies. If you're interested, you of course can develop your ensembling strategies and check our paper. But the main point is, we find that the self-ensembling actually works across all learning methods, including the inference-only methods and also the supervised tuning methods. And it enhances the calibration by over 40%. And also, it shows the power on supervised tuning methods as well, yielding much lower ECE score along with better in-task performance at the same time. And here is a more straightforward illustration for you to see. And if you can see that the right 2 diagrams are the system with self-ensembling strategies, and the left 2 are the system without self-ensembling strategies. And you can see that this is really obvious when it comes to applying the self-ensembling strategies with supervised in-context learning methods. The pink area is significantly smaller than the second diagram. And for different variations and ensembling strategies, we found that for inference-only in-context learning methods, the variations in context examples enhances calibration and performance the most. But for supervised tuning methods, the variation in prompting and combining both variations in context example and prompting may perform better than the variations in context example single. And I think we suspect this is possible because the prompting templates may be not optimal, so it requires to tune the model parameters to really fit in the model in this prompting templates. And for among 3 different strategies, we found that the widely adopted majority vote ensembling strategy may not be the best option in enhancing the trustworthiness. Instead, the max probability consistently enhances the trustworthiness as well as the performance. Yes. And we also deliver some evaluation studies with more ensembling components and with different sizes of training data and model sizes. And we find that the key findings still hold with these variations in the hyperparameters. And this the table on the right is the result with from T5 extra large with the 3 billion parameters. So here's a summary about the work. So for the first research question, how would in-context learning impact the calibration of large language models? We found that the language model with in-context learning is not necessarily calibrated, and the performance and calibration of learning methods are task-dependent. It's actually depending on whether the data has been seen by the model before. And we provide some practical guidelines on how to select the learning methods, considering both in-task performance and calibration at the same time. And for the second research question, we investigate and justify the feasibility of using self-ensembling strategies in enhancing both the calibration and performance of language models without sacrificing one of the 2. Yes, and that's all for my presentation. Thank you very much.
We have time for one question?
Wow.
alignment and calibration. So there's a big figure at the GPT-4 report which shows that after the pre-training and before fine-tuning, the model is well calibrated. But after the alignment, the calibration is just so worse. So I think there is a trade-off maybe between the alignment.
Yes, actually, when we do the experiments, we do observe the trade-off on certain data sets between the in-task performance and calibration. Sometimes if you really achieve a relatively high in-task performance, the calibration would become worse. But this doesn't hold all the time across all the data sets. And I think that's possibly because sometimes the model would, when you really tune the model, then the model would be overfitted in the data set you train them, so making the calibration even worse, although you're achieving a higher performance. Yes. And even the model I used from T5 in this work, they claim that they are calibrated during training. But it seems that when you have different prompting templates fed into the model, or you do a post fine-tuning the model, then it will become worse in calibration as well. Yeah. I hope that helps.
Thank you, Chengzu.
Thank you.
And let's welcome the next presenter.